Hey, this is DW. This morning's lecture did not get captured, so I'm going to go through it one more time here in my office, and that way you'll be able to study for the exam. This is Chapter 2 from my book proposal called Managing Messy Mathematics, and we're going to take apart a spectrum all the way down to the wave function. So instead of building this up from the wave function up to the spectrum like most books do, we're going to start and do this backwards. We're going to start with the data that we actually have in the lab, visible spectrum, and then we're going to tear it apart so that you can see what the math is behind the horizontal and vertical axes on a spectrum. And so to begin with, though, let's talk about last week's homework. I had you focusing on the energy level diagram because I know that you use those in organic, and we talk a little bit about them in Chem 2. And I just wanted to make sure that we understood two very important vocabulary words. Those are levels and lines. Just making sure that I have the correct video going. Yes. Okay, so what we have here on the right is an energy level diagram with three levels. The lowest level is the ground state. And then we have two excited states. E2 is the first excited state, and E3 is the second excited state. And we have three emission transitions here. So transitions are jumps between quantum levels. In fact, this is one of the things that made Schrodinger so upset. He didn't have a model, and we still to this day do not have a model for quantum jumping. It seems to happen instantaneously. And in nature, there really isn't any instantaneous. The speed of light would be the fastest thing that could happen in the universe. But these quantum jumps seem to happen instantaneously, and so that's still a quantum mystery. But if the jump is from two very closely spaced energy levels, let's look at this one here. You know, this is a short arrow, and it's between two levels. So the energy levels are different than spectral lines. So we need to pay close attention to those two words. They both have energy units because a spectral line has a difference between two energy levels. And so it still is an energy unit, say joules, kilojoules per mole, wave numbers, could be frequency as well, but what we have is a difference in energy levels gives us a spectral line. And if you'll notice that if the energy difference is small here, then we have a low energy difference, which means a low frequency, which means a long wavelength. And so you need to understand these relationships, and those need to be you need to be very comfortable with those. Notice how the longest jump here is the largest energy difference. That's a high energy difference, a high frequency, and a short wavelength, and that's what we have in this wave here. It's got a very short wavelength, a very high frequency, and that's the kind of light that would be emitted from a quantum jump that was a very long jump from a high energy level all the way down to the ground state. So what we have here is just the same text that tells you what I just said. So let's start with some visible spectra, or different kinds of spectra that we'll see in this course. This is one of the spectra that we're going to have in this course. It's the infrared spectrum of automobile exhaust. We see several of the combustion products here. We have CO2, and we have water, and then we have incomplete combustion, which leads to carbon monoxide. Let's zoom in on that spectrum. And isn't that amazing? These are individual rotation and vibration lines. So this is the vibrational transition right here, and then these are rotational lines. So these rotational transitions are differences between rotational lines, and so rotational motion is quantized as well. Vibrational motion is quantized. Also, we do see that if it's in confined space, like an electron in a box, then you would think about that as quantized translational motion. Well, really, it sort of becomes a vibration if it's in a small space. But this is a realistic spectrum. This is a spectrum you're going to analyze in the course. Now, one thing about this spectrum, let's look at the y-axis. This is absorbance, and so this is the a tall peak means it's absorbing more light than a shorter peak. And then down here at the bottom is transition energy and wave numbers. So what is a wave number? Well, if we take a transition energy, the difference between two energy levels, we can get a delta E. Well, that can be using Planck's equation equal to h nu. What's nu? C over lambda. Okay, so that can be equal to hc over lambda. Well, if I just bring these two constants over and write out my energy, my transition energy over hc, then I end up with 1 over wavelength. And so that's what's being plotted here. It's the transition energy converted to wave numbers. If I use centimeters per second instead of meters per second in my speed of light value, then I end up with inverse centimeters, which is wave numbers. And so at this point, right here, for that frequency, that is actually 2100 wave numbers, and that means there's 2100 waves in a given centimeter. That's the gauge of the frequency of light. And so typically we will write this as frequency but with a tilde on top. And so that's another designation for transition energy. We would write that as frequency, but it's really not frequency, it's inverse wave number, or inverse wavelength. Here's a visible spectrum, or UV visible spectrum, of 3-nitroaniline. And so going back to organic, so that's the molecule that we're looking at here. It's a colored molecule. The visible spectrum starts here at 400, and so we're losing some blue light here, so this is a yellow molecule. But we see three main features. We see a transition here, we see a transition here as a shoulder, and then we see a big peak here. And so you would look at this spectrum and you would see that this is the visible region. This is UV. So you would see this particular spectrum and you might say that there are 3 peaks in this spectrum. But actually there might be quite a bit more, we just don't resolve them. So let's get away from such a complicated molecule and go to the particle in a box visible spectrum. So this is actually a simulated spectrum of an electron confined to a 7 angstrom box. And so what we have here is a theoretical spectrum, one that we've created and that you will create in the lab, that you will analyze in the lab. And so we have 3 main features that you would imagine if you looked at this curve. But in fact, there's actually 120 transitions underneath this curve. And so we're going to look at those here in a second. This is the UV visible spectrum of an electron confined to a 7 angstrom one-dimensional box, and it has the intensity pattern that it has because it's at a very high temperature. There are a lot of excited electrons in this particular system because it's at 500,000 Kelvin. So let's look at this spectrum with this intensity equation in mind. So if you'll notice, there are several parts that might add up to create the vertical axis. So let's look right here at this relative absorbance axis, the vertical axis in this spectrum. You know, what gives us this pattern of peaks? That's given by this equation here. And so what we're looking at is the summation at each individual wavelength. We have the summation of a line shape formula, some sort of intensity factor, and this Boltzmann factor here. And this is a summation at each given wavelength, and that's summed, or that intensity that's added up at each wavelength gives us the total absorption profile. So the absorption intensity is a function of the thermal effect, here given by the Boltzmann factor, a probability effect given here by the transition moment integral, and then the line shape effect, which is determined by several things, partly determined by the instrument that we use. So let's look at these individually on the spectrum. So here we have that same equation and all the pieces are broken apart. So the overall absorption profile is right here. It's given by this curve. The Boltzmann factor here. Okay, so that's this right here, and that's this curve that's going along and getting smaller and smaller as we go to shorter and shorter wavelength. The Boltzmann factor determines the temperature dependence of the population of those energy levels, and so as they get higher and higher above the ground state, they're less and less likely to be populated, and so we see that in this Boltzmann factor as it drops off down here at higher excited energy levels. We have the individual intensity factors here, and those are given by these lines right here. In fact, let me try to color code this. So then the green would be this one here. Okay, so these green values are the probabilities of each transition. And the first three are pretty similar, but you start to see those probabilities taper off. Now this first transition is the probability of going from n equals 1 to n equals 2. So this is the fundamental transition, the very first one, the longest wavelength transition. And it's from energy state 1 going to energy state 2. This next one is going from 2 to 3. The next one's going from 3 to 4, etc. Notice how we don't resolve all of these peaks down here. They run together and give us this large peak. Let's change color and look at the Gaussian values. So let's do orange. So now we have the peak shape, this Gaussian function here to give us the shape to our peaks. And so this Gaussian line shape is given right here. It's this bell curve that we see. Now if you'll notice in the text version of this chapter that I passed out or gave on Blackboard, there are other line shape functions that we could use. There are Lorentzian functions. There's a combination of a Lorentzian and a Gaussian function to give what is called a Voigt profile or a Voigt line shape. And there's also log normal functions that you can use to give asymmetric peaks. So Gaussian is not the only one that we could use, but it's the simplest. And so it's also typically the one that we see if it's just the instrumental line shape that's governing the resolution of the experiment. So all three of these pieces, the intensity factor, the probability factor, the Gaussian line shape, and the Boltzmann factor contribute to the overall spectrum, and that contributes to the y-axis or intensity axis of the spectrum. Those transition moment integrals, those I values, are essentially the probabilities of light interacting with the wave functions to give us that transition. So let's look at this a little bit. Notice this is the, we've got some labels on these. There's A and S. One is for absorption and emission, okay, and the other one is for scattering. So pay attention to those superscripts. I just coming up with some terminology for you to keep track of the two. Absorption and emission have the same probability, and they're different than that of scattering. So what's happening here is this is the lower state or initial state wave function, and this is the final wave function, and this represents light. So how does the x-axis represent light? Well, if you take a particle in a box and essentially it's an electron on a wire, and this happens to be the x-axis, then light coming in with an electric field aligned on that x-axis can interact with the wave function. And so this x-axis has a positive end and a negative end, just like an electric field has a positive and a negative pole, and it can come in and can interact with this wave function. How do we know the interaction? Well, we just take x and multiply by that wave function, and it perturbs the wave function. Then we look at how this perturbed function, x times psi, overlaps with an upper state or final wave function. And so we have three functions multiplied by each other. We integrate them over all space, which in this case is just from the left side to the right side of the box. And that may give a positive or negative number, but intensity is related to the square of that integral result. And so if that integral result is large, then we have a high probability of that transition. If it's small, we have a lower or shorter peak, a lower probability for that transition occurring. And then if it's zero, we call that forbidden. So if this is equal to zero, then we call that a forbidden transition. If it's not equal to zero, it's allowed. And the same goes for the scattering. The scattering equation or probability is related to x squared. And one of the simplest ways to think about this is it's a two-photon process for scattering. A photon comes in, interacts with the wave function, and a photon leaves. So we need to take into account two electric fields, the electric field of the incoming photon and the electric field of the exiting photon. And so we have essentially two electric fields perturbing the wave functions and then having the final state wave function multiplied in. So we really have four functions multiplied by each other in the scattering example. But it's still, if it's a zero, it's forbidden. If it's non-zero, it's allowed when we do those integrations. Let's talk about the thermal population. This is the Boltzmann factor, and you'll notice that it relates to the energy. And so in this, notice I'm using the word initial and final, not low and high, because in an emission event, the upper state is the initial state. In an absorption event, the lower state is the initial state. And so you can't have a transition if there are no molecules in that energy level. So the Gaussian, or the Boltzmann distribution computes the probability of that state, that energy level, having molecules or electrons or whatever system you're talking about. Does it have any molecules in that energy level? If that energy level is not populated, then there won't be a transition, no matter how probable it is. And so then what we want to do is compare that energy of that initial state to the amount of energy available in the room, if you will. So this is temperature, and then this is Boltzmann's constant, which converts that temperature to energy. And then this is a degeneracy factor. There may be an energy level that is triply degenerate. So it has three states, three levels that have the same energy. And so this G value would be 3 for that situation. We see that in the 2p orbitals. You know, if you just do the simple Aufbau filling scheme, you would have 2px, 2py, and 2pz. And in the absence of electric fields or magnetic fields, they would have the same energy. So this is the degeneracy factor. And all of these things give us the Boltzmann factor for the transition. So that's what we would determine the thermal population statistics using the Boltzmann distribution. And then we need those energies for the Boltzmann distribution. So we need to find the energies of these quantum systems, and to do that we need the Schrödinger equation. So you may see this equation written in different forms, but this is the integral form of the Schrödinger equation. And so it has the Hamiltonian operator, which is the total energy operator, operating on the wave function, and it's left multiplied by the wave function and integrated over all space. The Hamiltonian operator has mass in it, and so this is actually where the particle is defined. You notice in the wave function, in a minute when you see the wave function, you won't see mass in the wave function. So the wave function is just telling us about the boundary conditions, but the mass comes in when computing the energy. It also has this second derivative operator, which is the curvature. So the first derivative operator would be the slope. The second derivative would be the curvature. The potential energy in our particle in a box system is easy. We set it to 0 inside the box and infinity at the walls of the box, so the electron can't leave without having infinite energy. So that's one easy way mathematically to make a bound system. The electron has to stay in the box because it's got finite energy. And inside the box, it has 0 potential energy. Everything's kinetic energy. Now this middle equation is the orthonormality condition. Orthonormal, or I'll say orthonormality condition. We will unpack this a lot more later, especially on Wednesday. But essentially it's saying that the wave functions need to be orthogonal, which is another way of saying they need to be independent from each other. You can't have the energy level 3 wave function for state 3 be the sum of the wave function of state 1 and state 2. So no wave functions are sums of other wave functions, and also any wave function times itself in integrated overall space. This wave function squared here in the middle is the probability distribution. And essentially that's saying the distribution of the electron in the box, and we'll unpack that some more as well. So if that's the probability distribution across X and we integrate that overall space, we better get 1 because we've integrated overall space, and we don't want to get 1.5 or 0.6. We want that probability distribution when integrated overall space. We want the probability to equal 1. Think of it as statistics. We've looked everywhere and we found our 1 particle. Now on the x-axis of our spectrum we have the transition wavelength or transition energy in wave numbers, and so we need to compute the locations of those peaks, and this requires a transition equation. This is a super important computation to perform for any spectroscopic system. And so it's a difference in energy levels. You have the energy for quantum state n, and you have the energy for quantum state n prime. You take the difference between those to compute the location of a peak for the transition from n to n prime. And so that's going to give us our transition energy. This is the n prime level, and this is the n level. And so this transition energy can be converted to frequency, or it can be converted to wavelength. Notice that it's inversely proportional to wavelength. If I have a large difference in my transition, I have a very short wavelength. And then finally we get all the way down to the wave function. We've used the wave function in the transition dipole moment integral. We've used it in the Schrodinger equation to come up with the levels that we needed for the Boltzmann factor and what we needed for the transition equation. And so now we're down all the way to the particle in a box model that generated that spectrum. So we've drilled all the way down to the quantized system, and now you see the lowest 3 quantized energy levels for particle in a box system. And so here we have the ground state, we have the first excited state here, and we have the second excited state. Remember I said that kinetic energy was related to or proportional to the curvature of the wave function, and we see that the ground state wave function curves the least, the first excited state curves more, and we can test curvature by just counting the number of nodes. So this one crosses 0, so that's a node. This upper one crosses 0 twice. And so if it has more nodes, it's more curved, and that means it has a higher energy. So if you were to classify or rank, let's say, or order wave functions related to their energy, you put the ones with the most nodes at higher energy and the ones with few nodes or zero nodes down at the bottom of an energy level diagram. The non-zero areas in general are called lobes. And so we have lobes and nodes in our wave functions. Notice outside the box, the potential energy is infinity, and inside the box, the potential energy is 0. This is our wave function. Here we have our normalization constant, which you're learning about in lab this week. We have a sine function, which is an oscillating function, which is necessary for our second derivative operator. And then we have the x-axis here. We have the quantum number, and we have the length of the box. And so in our case here, our box is L equals 7 angstroms. And so we're plotting this from negative L over 2 to positive L over 2, so that our wave functions will be centered on 0. To get these wave functions to be centered on 0, we had to put in this phase shift. And that's to get the wave functions centered on 0. What you'll see too later on, or you've already seen this in organic, no doubt, that is, we would color the wave functions. Say if we're doing atomic orbitals, we might draw one particular part of the orbital as green and another part as red. And so let's say that all the portions above the average location of the amplitude are green, and the ones below that are red. So let me come back. And sometimes we might even label those orbitals as negative on some portions and positive on other portions. And I want to emphasize that we're not talking about charge. Okay, this is positive deflection of the wave function from its average value, or negative deflection at an instant in time from its average value. And so this is really important to realize, that when we're dealing with wave functions, we're dealing with oscillating functions, and at some time they're positive, sometimes they're negative, just like a guitar string. If you were to label one direction as positive and pluck the string and then took a snapshot, you would see some portions of the string that were in the positive direction and other portions of the string in the negative direction, but that didn't correspond to charge. It just corresponded to positive and negative deflection. It's totally arbitrary which is positive and which is negative in that respect. Also, these functions oscillate, and so the positives will flip to negative regions and negative regions will flip to positive regions, but the nodes won't change. And so the nodes are stationary. So I think it's we've done it now. We've taken the spectrum, we've pulled the thread all the way down to the wave function. And what you'll do in this week's lab is you'll start with the wave function and you will normalize it. So you will solve the orthonormality condition, you'll solve the Schrodinger equation, and you'll do these things by hand using that wave function that we had, that sine function. And then you will also later on compute the Boltzmann distribution. You won't do that this week. You'll solve this transition moment integral for emission or absorption, and you'll come up with the allowed and forbidden transitions. And then later on we will use numerical methods, Excel, and we will generate this plot. So you will build this spectrum from the ground up, starting with the wave function and coming all the way up to the simulated spectrum. This is a fantastic skill set that you will receive, because if you just take then the particle at a box energies out and you put in the energies for, say, Ro-vibrational transitions in carbon monoxide, then you could actually simulate this spectrum from first principles as well. So the tools that you're going to learn will not just teach you about the particle in a box spectrum, but with these same tools you could simulate and analyze any kind of spectrum that science can throw at you. So I think those are some valuable skills to learn, and you can learn it by starting with just one dimension, this particle in a box problem, and then you can expand it by analogy to three-dimensional problems. So that's today's lecture. Hopefully you enjoyed it, and I'd love your feedback in the comments. Thanks.